So the first point I want to make about artificial intelligence and the revolution that we're in the middle of is that it's largely already here. So AI is already everywhere. And in fact, the very best AI is in all of our pockets in our smartphones. This is really a revolution in progress and something that we as citizens and as individuals are very, very closely acquainted with on a day-to-day basis. These kinds of technologies, the smarts in smartphones, is what we mean when we say AI. But I want to orient you towards the terminology of various academic disciplines so that we're all speaking the same language when we speak of these matters. So artificial intelligence is the art and science of trying to construct machines that have the appearance of some useful cleverness or intelligence. That's the way that I and many others defined it. Machine learning is a newer and smaller discipline that's really about making machines that learn. They learn from data or learn from experience. And it's the intersection between these two things where we've seen the most growth in the last 5 or 10 years. And that's the idea of machines that learn to have the appearance of intelligence. So I want to give some concrete examples in each of the various areas here so that we're all thinking of the same prototypes, not just the same definitions. So IBM Deep Blue, the chess computer that famously beat Garry Kasparov at the game of chess, was a clear achievement in artificial intelligence. We had a machine that appeared to play this very complicated game better than a human player was able to. But that system didn't learn anything about the game of chess. Instead, it was carefully engineered to be something that searched over the possible board positions in chess and find moves that looked promising. In contrast, if you fast forward a few years to the DeepMind AlphaGo player, which recently has bested the world champions at the game of Go, this system had to learn to play the game. When we tried to program systems to play the game of Go, they never came close to human performance. But when we built systems that learned to play the game of Go through their own experience, finally we were able to build systems that were competitive with human players. But I don't want you to leave thinking that everything about machine learning is this sort of AI milestone. In fact, machine learning is a very practical industrial technology that is used in the most commonplace of settings. And in fact, the ability of automatic teller machines, of banking machines, to read handwritten checks was something that has been using machine learning since the late 1990s. But no one looks at a bank machine and says, AI has arrived. It's a very simple kind of thing. But I also want to call your attention to another academic and engineering discipline that is very important and sometimes confused with these other two, which is the field of robotics. Robotics is fundamentally about making machines that move autonomously. And until recently, robotics didn't actually interact very much with machine learning or artificial intelligence, except in the world of science fiction. There are, however, today, some noticeable promising things at this intersection. And one of the most obvious ones is the movement towards self-driving cars. These are, I believe, the first technical example of something that has the appearance of useful intelligence, that learns from the real world, and that moves autonomously. In some sense, finally some example of something that is really at the intersection of these three fields. And I believe that in time, we will be seeing more and more examples of things that fit in that intersection. But I also want to explain another term that you'll hear a lot of, which is deep learning. Deep learning is actually a subfield of machine learning, and I would say that today it is one of the most popular forms of machine learning and has been used in a great many practical applications. And although it's one of the things that is fueling speech recognition and image recognition and many of these technologies, it also is not a new thing. Even this classic example of ATMs reading handwritten checks, it actually used early variants of deep learning that have been around for decades. But the basic idea of deep learning is that it's a reimagination or a renaissance in a field called artificial neural networks, which is something that has been around since the 1980s. And what's new is actually our ability to use data and computation in more efficient ways and at a larger scale. And what deep learning has allowed us to do is allowed machines to learn how to represent information on their own without us having to instruct them on how knowledge should be represented. And the way that these systems work in cartoon format is that they're able to accomplish very complicated tasks, things that were very difficult to describe in rules. For example, telling the difference between a photograph of a cat and the photograph of a dog, by building a series of decision makers that learn to collaborate. So we as engineers do not program individual decision makers in an artificial neural network to make a decision. Instead, the pieces have to learn to work together in order to collaborate and collectively make the decision. And that's the sense in which these machines learn. The pieces of the machine learn how to fit together to guide the outcome that we've asked them to make. And the way that these systems work is that they learn by imitation. Fundamentally, that is the process. If we want to build a machine learning system that can tell the difference between a photograph of a cat and a photograph of a dog, what we literally do is we amass a pile of photographs of cats, a pile of photographs of dogs, and we tell the machine to distinguish between these two sets. That's the sense in which data drives machine learning. Just having a pile of photographs mixed up together is not something that is useful with today's technology. We must actually be able to say exactly what it is that we want the machine to do in order for them to learn to correctly imitate that behavior. And this has really come a long way, this very simple idea. And one of the things that was catalytic in all of this was the study of object recognition. And for many years, we've been running these kind of academic challenges to see how well computers could do at recognizing objects. And when I was in graduate school, computers could not tell the difference between a cat and a dog. They could tell the difference between a cat and a fire truck. That was the state of the art. But now we're actually at the point where machines are able to recognize thousands of objects at least as accurate as humans. And this transformation was really catalyzed by this revolution in deep learning, which happened at about 2011. And this bar chart here shows the performance of various systems on this academic data set over time. And that you can see by about 2015, 2016, these systems have reached human-level performance at this simple task of recognizing objects. But this is something that can be made quite practical. So, for example, in Google's photo search system, you can now search for an arbitrary object in your own photography library without having to have manually labeled things. I can search for my photos of Siamese cats, and the system automatically and privately is able to find the photos that I've taken of Siamese cats. And when it runs out of Siamese cats, it shows me other cats, because it kind of has the basic notion of what's going on. Now, this is very exciting, but it's not just about photographs of cats, although obviously I like cats a lot. It's useful in other domains that have nothing to do with photography. So one of the projects that I had the pleasure of working on was the updated machine translation system that Google uses. And if you looked at this machine translation system just a few years ago, it had a lot of problems. So for example, you could play this funny game where you could take a passage of text that you knew in your native tongue, translate it to some distant language. So for example, here I've taken some English, translated it to Japanese, and then tried to translate it back. And a few years ago, you got garbage when you translated back. This piece of Hemingway written in red at the end of the first passage is not intelligible at all. It doesn't make any sense. But fast forward just a few years later, and by using deep learning, the system has grown into a status where it can mostly get the translation right. It misses only the definite article on the word leopard, which is something that is often lost when translating to and from Japanese. And this is kind of an understandable mistake. And these techniques have proven themselves to be surprisingly general. At Google and other tech companies, we use this for a variety of applications. It is how computers have learned to see. It's how they've learned to translate things. It's how they've learned to improve our ability to identify spam or cases of fraud. It's also how all modern speech recognition works. Whether you're talking to your iPhone or your Amazon Alexa or your Google Pixel, they all use machine learning, and in fact, they all use deep learning to accomplish that task because it is the technical approach that works today. And indeed, it's even how we do some interesting science by allowing these machines to serve as tools for the scientific endeavor. And the way that these things have been used, there's no end of surprise. So this is an example of a hacker who lives outside of Tokyo who used artificial intelligence to build a cucumber sorter for his parents' family farm. And this is something that one person can do by downloading some open source software and training it by example, by having his mother sort cucumbers the way she likes cucumbers sorted, and then having the machine learn to imitate the categories that she has demonstrated. But a question that I get a lot is, why is this all happening now? If artificial neural networks have been floating around since the 1980s, why now do we see this technical innovation? And the answer is actually something that reminds me of the human quest for powered flight. In the 1890s, there were people all over the world that had pretty plausible designs for flying machines, but none of them were getting off of the ground. And we didn't really at that time understand why. And the answer was a little bit surprising, was that the weak link was actually the power to mass ratio of the internal combustion engine. Engines were too heavy to push flying machines into the air. And the first people to fly were people who built their own custom engines to be as light and as powerful and short-lived as possible in order to push them into the air. But fast forward 10 or 15 years, and these engines are available everywhere. And people all over the world are able to build their own flying machines. This same thing has happened in AI. But rather than the 1890s, it was the 1980s. We've been sitting on ideas for how to do this, and we were waiting for the engines. But they aren't combustion engines, they're computational engines. And it's through the natural scaling of the increase in computation in CPUs, the realization that graphics cards can be reused for cheap scientific computation, and now even tech companies building their own custom silicon chips that accelerate machine learning even more, that drives this kind of change. But I want to underscore that, like the internal combustion engine, these are general use technologies. There's nothing specific to AI in these things, but instead it's about producing computation that is useful in this context, the same way that an engine is about producing torque that is useful in many contexts. And this has really grown particularly quickly with the advances in cloud computing. People now no longer need to set up their own data centers in order to experiment with these things. Instead, this has become a commodity. And this is part of the reason why hobbyists are now able to use these systems in order to build things that they find interesting. So I want to kind of go through what I think the central ingredients are in making these AI systems work so that you can identify for yourselves how we can facilitate this and drive it into the direction that we believe is most beneficial for our societies overall. So this one element that I've talked about so far that's so important is access to computational resources. And this was, for a long time, the missing link. But there are other essential ingredients as well. So one of them is access to good tools and algorithms, software in order to do this. And until just a few years ago, maybe 4, this was actually something that also impeded the progress in this field, which is that there were only a few companies and advanced labs that had access to good software on this. But recently, there's been a movement towards broadly open sourcing all of the software that goes into this. And at Google, we ourselves have open sourced the core software that we use for all of the applications that I've shown you. But it's also very important to recognize training examples, or in other words, data. These machines learn by imitation, and so they have to have examples to learn to imitate. But in my experience, it's actually the 4th ingredient that is currently the rate-limiting step in the advancement and deployment of these technologies, and that is human creativity and ingenuity. Because this is not a rote process. It is actually a craft. And what we are doing is we are training a new generation of craftsmen who are familiar with the ability to make new things using these tools. But I want to go back for a moment to talk about data, because I know that this will be another big topic for us today. So I want to show you this graph that I've made that is my subjective impression about the relationship between data and the quality of machine learning technology. It is true that having more data is helpful, but there are diminishing returns. And that as more and more data are used in a machine learning system, yes, it does sometimes make it better, but it's by smaller and smaller increments. And the amount of data that's required to actually change the performance in a meaningful way continues to scale in kind of a logarithmic fashion. And how much data is required to make a satisfactory product depends on the application. So when you look at a task like spell checking, there were actually already very decent spell checkers that didn't use machine learning at all. But it's true that today we have ones that are slightly better by using data and machine learning. And then there were other things like spam detection, which were kind of okay, but have gotten much better, which is we're thankful for, because spam has gotten that much better and more powerful. And then there are examples of things that were basically not possible without machine learning. Things like speech recognition, where the systems that did not use machine learning did not work very well. But it's still true that once you reach a certain amount of data, a certain number of hours of speech in any language, machine learning systems will learn to accomplish this task, and adding more data only leads to marginal improvements. So with these 4 ingredients together, though, we've seen people do some really remarkable things. So scientists, for example, are using this kind of technology to learn how real biological brains are wired. And they're doing that by building machine learning systems that can learn to trace the individual fibers inside an electron micrograph of the brain. At the opposite extreme, we're also seeing this have applications in astronomy, where people looking for planets going around distant stars are doing this by training a machine learning system to look for the subtle dimming and brightening of stars in the heavens. Something that if you tried to do it manually would just be intractable. In my own group, we're also using this kind of technology to try to build healthcare applications. For example, there's a tremendous shortage of doctors in India to diagnose a common complication of diabetes called diabetic retinopathy. And what we can do is we can use a machine learning system to distinguish healthy eyes from sick eyes in much the same way that we use them to distinguish dogs and cats. And what we've shown is that doctors can teach the machine to do the task at a satisfactory level. But it's important to understand the role of safety and fairness in all of this. So this is something that I'm very glad that there's a good amount of academic work going on, but we're just getting started. And we really have to attend to how we can make AI systems both safe and fair. And there's a lot of work to be done here, but I believe that this is an area where policymakers and engineers can really come together. And just in closing, I want to say that my own personal opinion is that the analogy between human intelligence and machine intelligence is kind of like the relationship between birds flying and planes flying. They have some things in common, but there are fundamental differences in the way that they work. Yes, they both have wings, but they use different techniques. And this leads me to have my own opinion about the relationship between what we feel is our natural organic intelligence and the distant idea of artificial general intelligence that we're all familiar with from science fiction. And I think that if you look at what machine learning is today, it's like a pair of pliers. It's something that does one specific task very, very well. And indeed, if you want to pinch things, there is no substitute for a pair of pliers. My personal feeling is that the AI of tomorrow is going to look quite different. It's going to look like a much better pair of pliers. And that's important because these technologies really are useful. But my opinion is that we are still quite some distance from the idea of a general, flexible, scientific intelligence. So just my conclusions for you all to take away. This differentiation between AI, machine learning, and robotics is very important. It's the idea of machines that have the appearance of intelligence, machines that learn, and machines that move. Currently, machines learn best from examples. And although deep learning is a very popular and effective ML technique today, this is not the end of the story. It's just the current era. And although this is only sometimes used as the term narrow AI, which is AI that is basically doing one particular thing, it's fundamentally some kind of pattern recognition. But this pattern recognition is really very useful. Why is this happening now? It's happening because computers finally got fast enough, and making AI work does require these four ingredients: creativity and ingenuity, cheap, fast computation, data to learn from, and tools and algorithms. And fortunately, most of these things have become broadly available. And yes, there are challenges, but these are challenges that we have to face together. Thank you so much for your attention, and good luck today.